Recording the session. Okay. Hello, everyone. I'm Ed Robledo. I'm part of the support team here for Autodesk Eagle, and with me is Jorge. Go ahead.
Yeah, I'm a support specialist here at Autodesk. So we're looking forward to working with you guys today through this webinar.
Hey, remember you could always find us on the forum. So if you have any questions, any comments, suggestions, or anything like that, we're quite often on the forum. So make sure you visit us on the forum. Okay. Excellent. So I'll be driving quite a bit of the webinar, and if you have any questions in regard during the webinar, go ahead and use the chat that we're going to have available, and we'll address the questions either in real time if it's necessary at that moment, or we will address the questions at the end when we have a small Q&A session. So I'm going to go ahead and switch lobbies and go ahead and do this. Okay. Okay. Eagle Pro webinar manufacturing systems check. This is what we're taking care of today. Okay, so let's go ahead and go to the presentation page, and let me go ahead and share my screen. I'm going to be sharing my second monitor. Oops, didn't have that there. Okay, so hey, George, could you let me know if my screen is being shared, please? Let me know what's going on.
Yeah, yeah, you're good, Ed. I can see
Good.
it.
Okay. So before today, the topic is all going to be about creating the manufacturer data to get your boards made. Okay. Um, this is a subject in regards of once you've already done, but I wanted to present some definitions before we moved on because it may get a little confusing. First of all, I wanted to be able to explain what's the difference between a drill and a diameter. When you're creating components in the Eagle Library Editor, usually you use pads. The same rule is going to apply for VS, points of transition that occur on the board as well. Okay, so the drill is actually the size of the hole that is going to be done on the board. It's actually the drill size. The diameter refers to the size of the plating material that is going to be showing up around the hole. Okay. In addition to this, I wanted to talk to you a little bit about what's called solder mask. I put a definition there on the page. You should be seeing it on the top right corner. That way you have an idea what solder mask actually means. Okay. Now, solder mask can be somewhat controlled from within the library editor. I'm going to go ahead and enable the solder mask layers in Eagle. The solder mask layer is the T-stop layer, which is usually layer 29. It's actually always layer 29 for the top, and layer 30 is for the bottom stop. Now, you'll notice that this shaded material that now appears on top of the pad, that's actually the exposed area. It's a negative, we're looking at a negative view of this. So whatever you see on the screen, that hatch material that you see above the pads, is actually going to be exposed. Okay, and it needs to be exposed. That way you could solder your components to it. Now, within the library editor, you have certain controls that are going to affect on the board. So let's go ahead and go to the properties of the pad. Okay, let me go to the properties, and on the pad, you notice that on the properties, I could control the diameter. Now, the diameter in this instance, I have it set to auto. And I'm going to be referring to this in a few minutes when we go into our design rule checks, because auto actually allows the user to have certain amount of control of the amount of plating materials on your pads directly on the board layout. The drill size is going to actually be affecting the amount of plating material that the pads are going to have. I have my pad shapes. It's quite common that we use octagon, or we could use maybe Y long or X long pads as well. Now, what I really wanted to talk here about was thermals and stop. These are these ticker points that we have off to the left-hand side. First of all, first it just means that you're identifying that as the pad number 1 pad for this particular component, which is going to take certain effect on the board layout later on. Okay, you don't have to do this. It's just quite convenient if you do. That way you could create some sort of an identifier to see which is pad number 1. Now, stop. The stop, this is an important one. I could have pads not have a stop. for the on the board layout. So if I select this option, you notice that the stop material disappears. Now, what's going to happen with this pad when I actually get the boards made? Uh, I'm going to go ahead and introduce another term here called tenting. This pad is going to be tented, or it's going to be covered with solder mask. So you're not going to be able to solder to the actual component. There are some instances that this is actually good practice, or it's a practice that could be done, not quite common. Okay. Now, thermals refers to if you have polygons defined on your circuit board, if the polygon is actually going to connect to this pad using thermal reliefs, which kind of like spoke-like wires, or it's going to connect to the pad by just simply swallowing it in entirety. Now, what happens is, and I'll be demonstrating this on the board in a few minutes as well. Now, having thermals is the most convenient way because you want to be able to be able to solder to this, and if you have thermals off, polygons will swallow it, and heat will dissipate too fast. So you won't. It's going to be very difficult to be able to solder the component. Having thermals on will create the spokes by which it's not the heat will not dissipate as fast, and allowing you to solder to the component as well. Okay, very well. Okay, so this is what I wanted to talk to you a little bit about the board. Anything you want to comment here, George, on the board, on the library side? Okay, these are the main terms. We also have something called cream layers, but this is a through-hole part, so we're not going to be really talking about the cream layers at this moment. Now, I'm going to go ahead and move on to the board now. Okay, please remember we have the chat screen open, so if you have any questions throughout the presentation, go ahead and see them. Okay, so let me go ahead. I'm going to switch over to my board layout. Just that way I could demonstrate about the thermals and the not thermals. If you're not able to see my screen, please let me know. Okay. Now, we were talking about thermal connections and having not thermal connections. Okay. So let me see if I have one here. Okay. I'm going to go a little slow because I know the screens need to be able to refresh. That way you can see it on your end. This is a simple project. This is the TI Launchpad. It's a 2-layer board. And here is I just wanted to let you see where the thermals is actually activated, so the ground polygons are actually connecting to the pad using the spoke-like effect here as well. Okay. And here the polygon was not able to reach through the right side, but it was able to reach through the top, bottom, and the left-hand side of the board. Okay, so this is the effect of having thermals on or thermal off that will get current. Now, the most common practice is to have the thermals on because you want to be able to solder to the components. Now, okay, that's the simple effects that I wanted you to view on the library that actually affect the board. Now, I'm going to be going back to the control panel because there's some settings on the control panel I'd like to present to you first. Okay, so I'm going to head back to the control panel, to the Eagle control panel, and load this up. Now, on the Eagle control panel, we have it's subdivided in multiple sections. One of the sections is called Design Rules. Now, we have a nice variety of design rules that can be loaded on your board. That way, it will do the checks that are predominantly used on different circuit boards, depending on the type of technology you're going to be doing on your circuit board as well. We've had contributions by multi-CB as well as Euro circuits and W-Direct as well. If I expand these, you'll notice that we have quite a bit of selections there. And if I select any of them, I actually get a pretty nice description of exactly what is the behavior of this design rule checker. Now remember, these are kind of important because these design rules checks actually, if you load them into your working environment, will affect the outer router, will affect some manual routing, and will definitely affect your checks. So the criteria are going to be based on here. Okay, and I'll teach you how to load these DRC rules in a few minutes as well. Now, Eagle always loads the default DRU, which is this one here, the default DRC as well. Now, and later on, towards the end of the webinar, we're going to be talking a little bit about CAM processor, which are the different CAM jobs that we have. And the behavior more or less is the same here. If you notice, if I highlight the different cam jobs, I actually get descriptions right here on the right-hand side of exactly what is going to be my final product. And I'll get back to this towards the end of the webinar as well. Okay, now let's go ahead. I'm going to be using, if you wanted to load it on your end as well, I'm going to be using one of our example projects, which is the TI Launchpad here. Okay, I already have it loaded up. So let me go ahead and load to this board. Now, okay, so this is the TI Launchpad. It's a 4-layer board, a 2-layer board, I'm sorry. And turn on the bottom layer as well. And you notice that I'm not using the blending, so I could get the solid colors throughout. I've created a alias that way I could rat's nest my board without having the polygons. That way it makes it a little bit easier for me to take a look at the board. So I just got rid of the polygons. Okay, it's not really a big deal. Now, in this on this design, this predominantly surface mount, which the majority of boards are actually now done. Now this board was designed based on certain criteria that were set up in what's called DRC, or the Design Rule Checker. It's extremely important that you set up your DRC before you actually start working on the board, because this is actually going to be monitoring that you actually follow the rules either by the board house or the criteria that you wish to use. So we're going to go ahead and evaluate the DRC a little bit as well. Okay. So on their tools, under the tools menu, you'll see DRC. If you prefer to use the command line, you could type DRC here, or you could just go to the DRC icon, which is located on the bottom left-hand corner of the screen as well. Okay. And we're going to spend a little bit of time here. Okay. So first of all is they're using a design rule check, basically, that they've created. If I wanted to use one of the design rules that I have by one of the manufacturers, I could click on here, click on load, and that will take me automatically to the DRU directory, and now I could select any of the criterias of the DRU files that come with Eagle as well. Now I just wanted to let you know that many manufacturers are well versed with Eagle, and they actually offer the DRU file for Eagle for you to download. So you could go ahead and download, you could place it on the DRU folder of Eagle, and just go ahead and load that. That way you're following the criteria. Now try your best to do this before you actually start working on laying out the board in its entirety. You want this to be consistently checked. Okay. Now we're going to go to the Layers tab now. Okay. Now the Layer tabs is where we're going to go ahead and determine if we're going to be working with 2 layers or we're going to be working with a multi-layer, more than 2 layers as well. We have some values here which allows you to set up pre-preg and core. Now, does this really affect your board in regards of the design sequence when you're using the plus or the asterisk for pre-preg or core? Not really. Actually, the values here for the thickness of your layers are mainly for reference purposes. So it's always a really good idea to have the values that you wish to use based on your board house, but they don't really affect your board. So these are more for documentation purposes as well. Now here is where you're going to set up your layer. For this board, we're using a top and bottom setup. If you notice, Eagle is always going to work from the outer layers to the inner layers. Okay, so we go from layer 1, open parenthesis, 1 asterisk 16, okay, which is using core material. Okay, so if I was to have more than 2 layers, and then I work from the outside in, so my next layer would be layer 2, and if I was going 4 layers, then that layer would be 15. Okay, so here I have now go ahead and set up a 2-layer system. Okay, a 4-layer system. So now I have layers going from the top to the bottom. Now it's quite common for us to use the plus sign for the. Okay, did I get that right, George?
Mm-hmm.
Good. Okay, good. Now you could go ahead and set up your copper thickness if it's necessary, as well as the amount of isolation material that is going to be used between the lasers, which actually define how rigid the board is actually going to be. Now, if I was to going to be having um, internal, blind vias, as you can see here, just a simple example. I could go here and just go ahead and take a square bracket, 2, semicolon, and close square bracket. Okay. Now, with this setup I have here, I'll have vias that are going from traveling from the top layer to one layer deep as well. Okay. So there is a document folder in Eagle in the document folder that explains how to do different DRC layer setups depending of the scenario you want to do. Now, you got to be careful here. Using blind and buried vias can get a little bit on the tricky side. Not so much tricky, but troubleshooting wise, they're not as easy to manipulate. So if you're doing a prototype, I would avoid trying to use blind and buried vias in the meantime. You may want to consider doing it towards the end of your design cycle. Okay.
Yeah, they're also crazy expensive.
Oh, besides that, yeah, they're not really economical to make either as well. Okay. Now we could also buried vias are vias that could travel from one internal layer to the other internal layer. Let me see if I could create a blind via environment right here real quick. That way you can see how it works. Let me see. Would it allow me to do that? Oh yeah. Okay. So if you notice, I have one via that travels from the top of the board to the bottom of the board, and then from the top to the board to one of the internal layers, and then I have another via sequence that goes from the top of the layer, from the top of the board, from the inner layer 2 to layer 15. Okay, so these are the different easy combinations that could be done on your layer list as well. Okay, now remember, you get creative with this. Why? You get a lot more real estate space, so your boards could be that much tighter. But then again, your boards are going to cost that much more to make, and they're going to be that much harder to troubleshoot as well. Now here's a topic that we're going to spend a little bit more time here, and hopefully I could use this board that I have in the background to use. By default, we use some very, very high values here. If you use a default, if you're loading up a brand new default board, you'll get all these values set to 8, which is extremely very safe values. But with today's technology, 8 mils is just way too big. So here you'll notice that on this board, they use 6 mils throughout the entire board. Now this defines what is going to be the trace. I'm going to go ahead and click cancel here. I'll refresh a little slow, that way your screens could go and catch up with me as well. Okay. So clearance defines exactly what is going to be the allowed size that remember, DRC controls the outer router and also controls our new router, which is the obstacle avoidance router. This actually controls it as well. Okay. Now, if you're doing manual route, without enabling the obstacle router, it does not control it. So it will allow you to do virtually anything you want to do. But DRC, when you run DRC, it'll let you know if you have any type of violations or not. So here we're controlling the distance between the clearance between my traces. This one will control the distance that I want to keep between my surface mounted pads, like this one here, on this cap here. It will control the distance I want to keep between my pads, as well as my traces, as well as my through-hole pads. As you can see here, my through-hole pads to my traces as well. That controls that as well. My vias are my points of transition. This controls how close I want my vias to be to my traces as well. Here is what type of flag. It's going to flag my distance between pad to pad for surface mount and through hole, and my distance between pad and vias, our points of transition for through hole vias as well as surface mounted vias. So here we go. Here's a surface mount pad, as you could see here for this cap. Let me just close the screen really quick. This is a great example right here. We have our cap, And here is my cap, and here's a VS. So it's going to make sure that I have at least a 6 mil, which this definitely does have it. But it makes sure that this distance, this clearance value, is actually from this pad to here to at least to be 6 mils. Okay, if it was below 6 mil, DRC would flag it as well. Okay, and the outer router will actually will take this parameter into consideration while the outer router is running. And here we have between vias in this for this board, we're using 8 mils. Now here on the bottom are for signals with for pads for components that are carrying the same signal. Okay, so these are set to 6 mil, which are very safe values as well. Okay, so if I have two surface mounted pads that are carrying the same signals, I'm letting Eagle know that do not, if it's 6 mils or greater of distance, do not flag that as a violation. Okay, and that's if they're carrying the same signal. Don't confuse if it's carrying the same signal to different signals. Okay, they're very, very different parameters. Okay, same thing goes for signal to pads, SMDs, as well as from VS to SMDs as well. Okay, we just host it again. Okay, so we were here talking about the DRC parameters that could be changed that affect actually the final board. Now, let's talk a little bit about distance. Now, in this parameter here, the first one that you see under distance is the distance between copper and dimension will be flagged. Now, what's dimension? The dimension layer is layer 20. Layer 20 is actually restricts the outer router or flags anything that covers that goes over the layer 20, the dimension layer. So if you draw your board outline, you definitely want to do it on the dimension layer, layer 20. So let me just go ahead and flag it here. That way you can see it, what it is here. So here's layer 20, right there, the dimension layer. This is the layer that is usually, it's always used to define your board outline. Extremely important because the outer router will work around it. And if you do any type of manual routing and you go over it or you go too close to it, it will be flagged as an error or a warning to the dimension layer. Okay, so let's go ahead and go back to DRC. Systems check, manufacturing. Let's go here to where it says distance. So this distance here, it says copper dimension, is that I'm allowing that copper could go as close as 8 mil to the dimension layer. Okay, and that's a very safe value, even though our default is 40 mils, but this is a very good value. Okay, also on here in distance tab, you'll notice that we have a drilled hole as well. Okay, so that is the size that is going to be allowed between between two holes is at least 8 mils or greater. Okay, as you could see here on the things here. Okay. Now, in the sizes tab, this gets interesting here, Jorge. Okay. Now, the sizes tab is the minimum width. Now, this is the width that is going to be obeyed by the outer router. It's going to use a minimum width as well. If you have any traces below 6 mil, they will be flagged as well. Okay, and the same happens here when it comes to the minimum drill. Now, this minimum width that we have here, that I'm showing here, can be overwritten by something called classes or net classes. Okay, so I could have a minimum width assigned for the entire design, but if you go here where it says edit and go all the way down to where it says net classes, I could create, actually there's one here created, and these net classes values will overwrite my default DRC value. So this size that you see here, this width parameter that you see here, which is 8 mil, is greater than the 6 mil. So when I assign a net class to my traces on the to my connections on the board, they will overwrite the value. So as you can see, my grounds here are going to be at 8. Okay, anything that has the class power is going to be 8 mils, which overwrites what I have under DRC sizes. Okay, so I just want to let you know that you could actually overwrite your minimum by defining net classes as well. Okay, George, are we cool there? Okay, now restring. I'm going to need your help here, George. We had this talk today about restring. This becomes really interesting conversation because restring calculates. We were talking about this when we were talking on the library. Restring actually calculates how much plating material your pads and your via have according to the drill size that is going to be used for that pad of that via. So don't be confused if you're working on a part in the library editor and you've defined a particular diameter, but when you use that component on the circuit board, the diameter actually ends up being a bit larger. Got that, George? Okay. And
I'm gonna see.
so this is what happens here. So let me go back because I want to make sure everybody gets this clear. This is extremely important here. Now, you see, I could create. I went back to our original design, to our original library that we're working on. Here's the pad, right? And we've created it. It's calculated a pad diameter based on the drill hole size here. Now, if I go back to my board, what controls the amount of plating material based on the drill hole size is under DRC. And if I go to the restring parameter, okay, so the amount of plating material I'm going to get is going to be based on the size of the drill hole multiplied by the percent factor that I assign it. If the value, the calculated pad diameter, exceeds that one from the library, and then it's going to use the calculated restring value. If the value assigned to the pad diameter in the library was larger, then it will use whatever larger value it calculates. Okay, so if I define a pad diameter on the library to be, let's say, 32 mil, and the calculated restring is 24 mil, well, the pad diameter is going to show up is the 32 mil one. Is that right, George?
That's correct. And just to add a little bit more information, the calculation is pretty simple. As Ed was mentioning, you take the drill value and multiply it by the percentage. At that point, Eagle is going to compare it to the minimum and the max value. If it's within bounds, then that value will be used to calculate the diameter. If it's outside of the bounds, then Eagle will use either the minimum or the maximum depending on which bound was exceeded. So at that point, once we have defined the restring value, the finished diameter is going to be twice the restring value plus the drill. So as I was mentioning, the larger of either the library definition or what restring calculates, the larger of those two is what's going to win. So in the example he gave, if you define a 24 mil diameter in the library, but restring calculates 32, Eagle's going to go with the larger of the two. In this case, the 32 mils. So you can always adjust these parameters to get the size that you want, or more commonly, basically you adjust the restring so that your settings just went out. One of the things that's kind of complex about restring is that it's global. It affects all of the pads, vias, and micro vias of your design. So you generally only want to modify it as much as necessary to get your settings to win.
Okay, cool.
Okay.
Yeah, so you do the same thing for your pads as well as your VS, okay? And remember that these parameters affect the entire board, okay? So these are global parameters throughout the board as well, okay? Now, micro VS are, we'll have to go into that on a different occasion. Micro VS, just to let you know, are VS that go, if you have BGA, ball grid array components, they go directly on the center of the ball grid array pad. They go in the dead center, and they'll go down whatever layer amounts you want to go to. Now, to have these work, you need to have blind and buried VS set up already. Okay, so this controls how much plating material is going to be used for micro VS as well. Okay, for BGAs as well. Now, here shapes. We're not going to really get into it because this is actually done more within the library setup. More, if you the roundness that you want, usually you define this on the board and in the library editor. You don't really define that here. Okay.
Yeah, however, in the at the beginning, remember how you showed that first pin?
Hmm.
Remember that parameter? This is where you would adjust it. So if you notice for pads, he has an option called first, and you can globally set that to be a shape other than the default shape you were using in the libraries. So it's not a feature that's very commonly invoked, but it can be useful. Basically, in the case of where you usually will have all of the pads in the package be the same, you can still define which one is going to be the first one. And in the manufacturing scenarios where they use that as a guide for orientation, you can just very quickly adjust the first setting here and make it something different than what the rest of the packages use. Like I said, it's not a commonly used feature, but it is there if it's something you need.
Excellent. Thank you, George. Now, I gotta move on, and we gotta go a little faster than this. I'm way over the allowed time that I want to go over. So there's just a few more settings I want to do. So let me get into an area here that will allow me to demonstrate this really quick. Okay. Now, on the DRC, we went ahead and I wanted to show you the supply. Now, the supply is the behavior that the connections are going to have on a board based on your polygons. So your supplies are actually your polygon pores. Okay. Now, if I want my vias usually are just swallowed by the polygon. Now, I could have vias with actually have thermals to it. So if I go ahead and I select this option, right, generate. Sorry. Okay. So I could click here where it says generate thermals for vias and click on apply. Okay. Cancel. That's nice. Okay, give me a second. Okay, so here we go. So by changing the DRC supply tab, I've told I want my vias to actually have thermals. Okay, so now instead of being swallowed, the vias being swallowed by the polygon, they're actually getting thermals. Now I can go into the properties of the via, and I could tell it that um, so I could go. Okay, cancel. Give me a second. Isolation. Okay, so I could go here and tell it not to generate the thermals for the VS. Okay, and click on apply, cancel, and I could go to the properties of the VIA. Um, I thought I was be okay. So okay, very well. So that's how the you could have that behavior switch between having thermals for the VIAs. Now it's not common for the VIAs to actually have thermals. Okay, let's go back to DRC. And now let's talk a little bit about about the mask. Okay, so to see this behavior, let me go ahead and enable the mask layers here as well. Okay, so if you notice my pads, my through hole pads and my surface mounted pads, they all have mask as well. So let me go ahead and go to the DRC. And if I wanted my vias to have mask, I could just set a limit here. Let's say, for example, here they have a limit of 15. If I set this to 1 and I click apply, you'll notice that my vias now acquire a mask. But in this instance, we want the vias to be tinted. In other words, we want them to be covered. So for then they set a value of 15 and apply. So now, because these vias have a drill hole size of I think it's 12 mils right here. Study this. Yeah, they're 12 mil drill holes. Since I set my limit, since I set my limit to the 15, since I set my limit to 15, anything below 15 will then be covered with solder mask, all of my vias. And here I could set the values that I want, the distance that I want here. Well, you see here, stop. Let me zoom in on this part really quick here. Okay, so here you'll notice that this, mask. These values here are the parameters that are going to be used to calculate the distance between the pad and the amount of isolation there's going to be, not isolation, but the amount of mass there's going to be. What is this distance from here to here as well? Okay, so that's what these are doing. And this is for the cream layer. Now, the cream layer basically is almost the same thing as a solder mask, but they only apply, let me turn off these layers and turn on the cream layer here. This only applies to surface mounted pads, as you could see. And for now this value, if I increase this number here, it actually doesn't go further away from the pad, it actually shrinks it. So because you want this value to be either the size of the pad or smaller, because usually SMD pads are so much tighter on complex components that you want this to be the same value of the SMD or smaller. Okay, so as you increase this value, you notice that it actually shrinks here as well. Okay, so if we have components, let's say we actually have one here, which is a great example right here. I'm going to just do a quick demo here. Let me turn on the stop layer. I'll disable the cream layer and turn on the stop layer. You'll notice that there's overlap on my mask here. So if actually you were to solder this component based on the mask layer, you could actually have them short out by mistake because there's nothing stopping the solder to leak over. Is that correct, George? So you have nothing leaking over here as well, okay? And that's why usually for SMD parts, the cream layer is the one that takes precedence for your layers, okay? Now, this takes care of DRC. We're basically done with any DRC. If you have any questions, go ahead and post it on the chat group, please. Now let's go through the post-processing now. So we went through all the definitions of what DRC and what DRC covers and what areas are mostly to be concerned. And to be honest with you, clearance is your number one concern. And you want to do this before you actually go to the board. Now we're going to go through the CAM processor. Now I'm going to go back to the control panel because I want to evaluate some of the CAM jobs that Eagle comes with already. Okay, so I'm going to go control panel. And here we're going to see the CAM jobs that Eagle has. Okay, I'm going to go ahead and expand this. The Exelon CAM job, these are like batch files. Okay, and these are a description of what these batch files do, but they have a graphical GUI, of course. They're ran through the control panel, through the CAM processor, I'm sorry. And here we have different setups. This is a Gerber for 2 layers. And if you look at the description is on the right-hand pane, and these are the extensions that are going to be given to the file when your Gerber file gets created. So you have your component side is going to be the name of the file with the extension CMP. This is your copper component side. Your inner layer is going to have the extension .ly2. It's going to be the same layer as your board with the extension ly2. And this is important because every now and then we've received calls, somebody that they created the Gerber files, but they're not really sure exactly what each Gerber file stands for. And this gives you a really nice description of what is each Gerber file stand for based on this extension. Okay, files are going to have the exact same name as your board. Files are going to be located in the same directory of your board, and they're going to have the different extensions. And we'll go through that exercise right now. Okay, so these are different ones. The one that we use, well, the one I use the most, I don't know if Jorge uses the same one, but I use this one, yes, because it creates all of the data files. This was basically based on a recommendation from a board house. That way we separate, it does all the Gerber files, top, bottom, it does the milling layers for any slots that you may have, as well as it does my drill files, plated and non-plated as well. Okay, so how do we go Gerber files? Let me go back to my board. Okay. So now I'm going to go ahead and click on the CAM processor icon. And as you already know, I'm going to click on File, Open Job. Now here are the CAM jobs that I was evaluating just a few seconds ago on the CAM processor. So if you want to see a description of this, go back to the control panel. That way you can see what each one, how they behave or what do they do. Now when I load the cam job, you notice that I get multiple tabs here. Sorry, I've been way over the allotted time, so I'll do my best to not keep everyone sleeping here that much longer. Okay, now here is the different cam jobs that we have. So we have our component side, which consists of the top layer combined with pads and vias. You have your solder side, which is your bottom pads and vias layer. So if you notice, each tab pertains to a different layer combination. Okay, our solder mask layers are non-plated hole vias, as well as these are my plated hole vias, and these are my non-plated hole vias. Okay, so since I started the process directly from the board, I click on the CAM processor icon, it automatically loaded this board. If I had gone to the CAM processor before with no board loaded, and then you click on File, Open Board, and select the board that you wish to process. Look for your board that you wish to process. Since I've already done that, I started it. I'm going to go ahead and click on the button that says Process Job. Okay, oops. Oh, so it seems I made some modifications to the board, so it wants me to save it. Okay, now I'm going to get a couple errors here because in legacy wise, Eagle always, when you created your drill hole files, it always wanted to use your top as well as your I wanted to use the drill and hole layers combined together. In this brand new one, we've done some small modifications to make this separate. So if you see here, I got the error message saying, hey, you know what? You're creating a drill file, but you don't have the other layer selected. That's okay. So it's an acceptable error, and I'm going to click OK to the next one. Now all my Gerber files are done. Now I'm going to go back and see where my Gerber files are. If I go ahead back to my project, okay, you notice that my Gerber files are exactly in the same folder wherever my board is located, and the files actually have the same name as my project file with the different extensions that we had explained earlier. So we got my component side, and we got my cream layers. You got the plated through vias and drill holes, as well as the non-plated, the GPI, anything that usually the ones that end with an I are information files. So those you will not be sending to the board house. They don't really need them. These are just information files. Your milling is for all your slots. That's where you define all your slots on the board on the milling layer. And then you got your silt screen layers as well, your copper bottom side, and then you have your solder stop, mask top, and bottom here. So these are what the layers look like. Okay. Now, I'm going to go ahead and use a program that we prefer. Actually, the one I usually use is ViewMate when I'm working on a Windows environment. So I'm going to use ViewMate. It's a pretty nice Gerber viewer. So let me load that up here really quick. Okay, this is really nice, easy to use a Gerber viewer. You could get this at penalogics.com. It's a free Gerber viewer. And I'm going to go ahead and load my Gerber file. Okay, so I'm going to click on File, Import Gerber. I'm going to go ahead and select, I got to navigate to my folder. Examples, projects, DI Launchpad. And I'm going to load the first thing I want to load is my silt screen layer. Okay, so my PLC file, my top silt screen. That's what it looks like. Let me see if I could change the color really quick. Go with a little bit of a grayish color, kind of a whitish color. So this is what my silt screen. So if I was to send those Gerber files to my board house, this is what the silt screen is going to look like. Now I'm going to go ahead and load my top copper layer as well. Import my Gerber file. I'm going to load my CMP file, which is my top copper. So this is basically what it looks like. Now, I'll go a little slow. That way my board loads at the same time as well. I'm going to go ahead and load my board. Sorry, too many screens open at the same time. Sorry about that. Okay. You guys let me know if you could see this. You're good? Okay, cool. So here, I have some aliases defined here already for when I'm gonna do this type of demo. So here I'm just zooming in on the same portion of these are my Gerber files. Okay, these are my Gerber files. Yep, this is my Gerber file, and this is my board file as well. Okay, so here you'll notice that this is, oh, I don't have the silk screen. I don't have the silk screen layer turned on here, so um, that's why they don't look identical. But this is only the copper layers, okay? So you'll notice that you could see my different pads here. This is my Eagle file on this side. These are my Gerber files on this side. And we got a really good match going on right here. You could see the behavior of the polygons through outlining the different parts. See, and you have connections here from the polygons to the surface mount, which is exactly the same behavior here. Okay. And this is basically what you expect to get back. So I really always recommend using some sort of a Gerber viewer to take a quick look at your Gerber files when you create them. Now, additional files that you could be used is from the Eagle. You could use a couple of ULPs. There's one called a Mount SMD. The Mount SMD. So how do you run that ULP from Eagle? Click on the ULP icon, and you get a list of them, and just look for the one called Mount. And the Mount SMD ULP, this one, Mount SMD right here, will create all the centroid data. That way you could use a pick and place machine to get your boards populated. Okay, so once you select it and you just click open, the files are going to be located in the exact same directory wherever your board is located. It's going to have the extension MNT for all the components on the top side of the board. And if you had components on the bottom, it's going to create a file called MNB, which are all the components that are going to be on the bottom side of the board. Okay, so in essence, once you're done with your board, this is what you should be seeing. Something like this. Okay, so I tried to do a little view here. That way you could see the same part that we're using here is that same part that we have here. We got that little marker there. As you can see it right there. It's on the corner of the part as well. You got your polygon fills, and you could see that we have that in Eagle, as well as we have that here on the Gerber viewer. Okay, that takes care of this session. Hopefully everything worked out. Sorry I went way over the time, but it's just a really, really extensive topic, and to be able to do it in 30 minutes would be quite difficult to do. And I'm trying to be as detailed as possible. Any comments, George, that we need to add to this?
I think we're good. I mean, definitely we could have gone into all the other UOPs we can use for manufacturing, but we don't have time for that one. We're going to have to do another one.
Yeah, we'll go ahead and do a part 2 as well. So let me just do here common, so that way you could see. This one actually has another layer here, which is that they're using the document layers as well here. So you could see how it matches the holes, as well as all of the identifiers they use, and all of the notation they use to define the different parts on the actual board. They're actually here as well. Okay. Sorry, I wanted to load more of the Gerber files, but it was getting a lot later than I expected it to go. So if you have any questions or any comments in regards of what we have talked about here today, please go ahead and add that to the chat group. We'll gladly go ahead and answer them. You could always reach us at support.eagle@autodesk.com. That's support.eagle@autodesk.com. And we'll go ahead and answer your questions. And don't forget, you could always join us on the forums. We always like being there and taking care of your questions. Okay? Session has been recorded. I don't see any questions, any comments, George. And the only ones I really see are the ones from the audio that we have there.
Let's see. Is it planned to support the export of IPC 2581? Our manufacturer strongly asked for this format to support automated data exchange for testing environments. So we do have plans to support some form of those types of formats, IPC 2581 or ODB++. So we are looking into that. We don't have an estimated timeline at this moment, but we do have plans to improve in that regard, because we know that that's kind of where everyone's headed. So
Yeah, it's an important part of post processing. It's become
Mm.
quite a bit of a standard, so yeah, it's being considered as well. Okay, so I'm gonna stop the recording now. But if you have any questions, go ahead and please